Assalamualaikum. Our group today will present about Lab 2 operational amplifier. My name is HARITH bin NORHILIMI with matrix number 251091538. And this is my partner.
Assalamualaikum, my name is ADLI IKRAM bin MOHTAR. My matrix number is 2510911565.
The objective of this lab is to understand how different op-amp configurations respond to AC signals, to compare theoretical and simulated results, and to relate these behaviors to real-world, non-ideal characteristics of the operational amplifier.
So next, I will discuss about inverting op-amp. So this is a inverting amplifier circuit consists of LM741 connected to Vin 1 VPP 1 kHz frequency at the negative input, and the positive input is connected to ground, and the Vout has a feedback resistor of 33 kilo ohm resistor. So when I simulate the circuit, I found when the input is in positive phase, the output will produce in negative phase. When the input is in negative phase, the output will produce in positive phase. This shows the output is inverted, and get the output is around 14 VP. And the output is clipped due to negative feedback resistor. So this is the derivation of the inverting operational amplifier. From the calculation, I get the value is negative 33 volt, and from the experiment, I get the voltage is negative 14 volt. So the conclusion, inverting op-amp has a output that is inverted, and the output voltage is clipped since it has a feedback resistor from the output terminal. So next, we will proceed with the non-inverting operational amplifier. So this is a non-inverting operational amplifier circuit. Consists of LM741 connected to Vin 1 VPP 1 kHz frequency to the terminal, to the non-inverting terminal, and the inverting terminal is connected to 1 kilo ohm resistor and ground, and the output terminal is connected to feedback 10 kilo ohm resistor. So when I simulate the circuit, I found if the input is in positive phase, the output will in positive phase, and when the input is in negative phase, the output will in negative phase, but the amplitude is amplified to 11 volt, 11 volt VP. So this is the derivation for the non-inverting operational amplifier. From the calculation, I get the value is 11 volt, and from the experiment, I get the value is 11 volt. The conclusion is the waveform output has the same shape as the input, but the voltage is amplified.
Next, I will present experiment C, which is the integrator operational amplifier. The purpose of this experiment is to observe how an op-amp performs mathematical integration and to compare the theoretical output with my LT-SPICE simulated result. This is the integrator circuit used in LT-SPICE. The input signal is 1 volt peak and 1 kilohertz square wave. In this circuit, the capacitor in the feedback bars forces the op-amp to integrate the input. It controls the input current. A 10 mega ohm resistor is added in parallel with the 0.01 microfarad capacitor to prevent drift. It is because the input is a square wave. The ideal integrator output should be a triangular waveform. This is the result from the part C. From the integrator formula, minus V1 divided by RSC. So the Vout calculated, we got minus 1 volt. While the Vout in experiment, we got minus 1.3 volt. The output waveform is a clean triangular wave, exactly as expected for the integration of a square wave. These results demonstrate the key principle of integration. A constant input produces a linear change in output voltage. During the high level of the square wave, the capacitor discharges linearly, which is in negative slope. During the low level, the capacitor charges linearly while in positive slope. The slope is determined by the RC time constant. Next part is part D, differentiator op-amp. The output voltage for a differentiator op-amp is given by the formula shown in the lab sheet. So this is the shown circuit of the part D for the differentiator circuit. When a triangle wave is used as the input, the output should be a square-like waveform because the triangle wave has a constant slope. This is the result and analysis of the part D. However, in the experiment, the output saturates at about -4 volt, while the calculated showed -1 volt. The peaks are clipped. The edges of the waveform show spikes due to fast changes in slope. This happens because of the op-amp cannot exceed its supply voltage, so the output saturates before reaching the ideal value. Why is there a 100 picofarad capacitor? The capacitor is added to improve circuit stability, reduce high frequency noise, reduce unwanted spikes at the output. Even though the ideal differentiator does not use this capacitor, a real op-amp needs it to avoid oscillation and noise.
So next we will proceed with the summing amplifier simulation. So this is the summing amplifier circuit that combine two input producing a single output. The first input is from the U1 and the second input is from the Vin 1 Vp with 300 Hz frequency. So when I simulate the circuit, I found the waveform is inverted with the input. When the input is in positive phase, the output will produce in negative phase. When the input is in negative phase, the output will produce in positive phase. The voltage amplified to 6 VBP. So this is the derivation of the summing amplifier. From the calculation, I get the value is -6 volt, and from the experiment, I get -6 volt. So the conclusion is the waveform is inverted.
So the conclusion is, in both the integrator and differentiator experiments, the op-amp produced the expected triangular and square-like outputs, confirming the theory. However, real-world effects like saturation, noise, and offset caused deviation from the ideal result. The added 10 megaohm and 100 picofarad components help stabilize the circuits. Overall, these experiments showed both the ideal behavior and practical limitation of op-amp application.